All right. So what do we have? We have an imine and coming from this alkene. So just basic analysis looking at this. If you see an imine, you probably need to start recognizing that it came from an amine and the carbonyl, and this is an aldehyde, right? So that's easy to go one step back, hopefully, to this aldehyde and this primary isopropylamine. What perhaps is a little harder to see or to think about, there's one, is, well, wait a second. So we have this alkene, and there's carbon 3 and carbon 2 in the alkene. And then we know, just even looking at this, there's carbon 3 and there's carbon 2. We need to put whatever's important, whatever we want to do, whatever functional groups we want to add, where do we need to put them? We need to put them on carbon 3 or carbon 2. We need to put them on carbon 2. Right? So if I look back at this alkene, there's carbon 3 and there's carbon 2. Which carbon would you say is less substituted? Carbon 2. Right? So you need to start, that should trigger in your head to think, wait a second, anti-Markovnikov stuff. Right? I need to add something to the less substituted side of the alkene. Those are my anti-Markovnikov reactions, right? Where the product, the OH, the Br, or whatever ends up on the less substituted carbon. That's what I want to do here. Okay, so that hopefully helped that popped into your head. So one way to do that, right? This would came from the alcohol. All right. Do you know how to make a primary alcohol from that alkene? I hope you do. You can go from there to there. Now in the forward direction, what reagents do you need? This is that BH3, step 2, H2O2. If I want to take a primary alcohol and oxidize it just to an aldehyde, what reagent do I need to use? That's PCC. Right, that stops at the aldehyde. And then here I need to add in H plus to get that imine condensation to take place. The key disconnection is to see, start to recognize, right, where do I need to add the functional group? Where do I need to add the electronegative atom that makes the bonds polar, right? Carbon 2 all of a sudden, it's important in the products. So you got to make it important moving forward in the starting materials. So for this one, you need to recognize when you're not given the product, you have an amine, a primary amine, and an aldehyde. That's going to turn into an imine. All right? Numbering your atoms is really important here to keep track of everything. There's your oxygen, 1. The 2 hydrogens that were here, right, end up on there, right? That's that whole condensation process we've done before. The only thing different now is that it's intramolecular, which maybe threw people off a little bit. But what's the first step going to be? The first step is going to be protonation, right? Protonation. Right? Acidic conditions. What do you do in first step in acidic conditions? You protonate. That makes carbon 2 more electrophilic. The lone pair on the nitrogen then reacts, right? After this has been protonated, it does that. Protonation first, then addition. Tetrahedral intermediate. You start working to get rid of the water and doing proton transfers. Okay? And you regenerate H+. So we've done that before. Acidic conditions, protonation. Right? First step. So you got to be able to recognize that. That's important. The next thing they ask us to do is they show a new reagent, but it's really not a new reagent. You should have an idea what it wants to do. What does that look like to everybody? You put a plus there, a minus there, right? And so instead of sodium borohydride, it's sodium cyanoborohydride. Whatever, right? Whatever. It's like H minus, okay? It's going to do reductions. So how is it going to react with an amine? It's going to be a little different. You actually can use H2, one of your old favorites, palladium on carbon. Remember seeing that with alkenes? What does that do? it takes our imine and it's going to add hydrogen. Cool. Right? It's a reduction. It adds hydrogens to carbon 2 and add hydrogens to the oxygen. All right, so it's a little different, but the same idea. Don't worry about the mechanism. But if you see these reagents, you can take an imine, and then turn it into a amine. Right? So that's a way to do this. It's called reductive, ready? Reductive amination. You did a reduction, right? You added hydrogens, and you formed an amine. Reductive amination. So, the next thing we're going to talk about is this dielectricization of amines. So, just in a broader sense, why are we doing this? What does it matter? So, if you look at what happened here, we've turned this amine into an N2. Now, why would we might want to do that? Well, if you see N2 like this, you should realize that's like nitrogen gas. And that makes it a good leaving group. Now, it's a little weird here because it's on a benzene ring, and we'll talk about that reaction in a second. But what we've essentially done here is we've taken something that's electron rich, a nitrogen, it's like a nucleophile, and what have we done to it? We've turned it into an electrophile, right? And thinking it chemistry-wise, that's really important, right? Taking something that is normally a nucleophile in one sense and then turning it into an electrophile, right? That can be a very powerful transformation, right? That's right. We're always thinking about who has electrons, who wants them, but being able to change atoms, reactivity in that way is important. Right, so that's the end big goal here that we're trying to think about. So how are we actually going to do this? So there's a really neat way to do it. So the way you do this is actually usually you start with NaNO2, like a salt, and you put that in acid or water, right? And you end up getting these two things. So you still have the acid floating around, H3O+, and then this has been protonated now. So now the oxygen has a minus charge. Now you have this nitrite, right? And so what's going to happen here is weird because this is H3O+. And if you see H3O+, what do you want to do? What should you always do? Use it. Have it react. It's an acid. It's a really, really good acid. Where on this molecule is it most electron rich? Well, it's going to be right there. Now this is where it gets kind of, I think, cool. So protonation. So we got water. And now we got this guy. Huh. And you should see that and be like, whoa. Water. That needs to go, right? And you need to add a nitrogen, right? If you look back up here, the whole point of this, we're creating this reagent to add this nitrogen. This one's nucleophilic. Wouldn't it make sense to make a nitrogen that has a plus, like maybe it's electrophilic? So what you can do, and they do it in stepwise fashion. I would do it all in one shot, but we'll do it stepwise. Kick the water off. So I have a nitrogen with a plus charge, right? Now, is this the best resonance structure? No, because it doesn't have a full octet. So you could draw another resonance form, which I think is better. It looks like this. Yes, the oxygen has a plus charge, but who cares? Everybody has a full octet. So it's a good example. When you see this, where is it actually electrophilic at? The nitrogen or the oxygen? Where is it electron deficient? So which one of these is actually electron deficient? It's the nitrogen. Again, just because you have a plus charge in the oxygen doesn't mean it's electron deficient. Right? Lewis dot structures lie sometimes. Who's more electronegative, nitrogen or oxygen? Oxygen is. Right? So that, even though the plus charge is there, this molecule is electrophilic at the nitrogen. So that's what's going to happen in this next step. Is the nitrogen is going to react like that. kind of adds in, breaks the pi bond. So now from here, what we need to do is essentially turn this into water. Get it to leave. And these are the things that you've done before. They kind of essentially a series of proton transfers. Right? So right now, the first thing you're going to do is a proton transfer. Right? So it's not quite the same as you've done with the imines, but it's the same idea. Right? So what am I going to do now? Well, move the electrons there. This is really like a resonance form. Oops. Plus charges back on this one. Do another proton transfer. We're getting close now, right? Plus charge there. And then the last thing we're going to do is kick that out. And that gets us there.